Let's continue from the steady state error. This is another important criterion for the time response because we have to consider steady state error. For example, you want from the motor it should be turning on with 500 RPM, but at the steady state motor will turn with the 400 RPM. So here we have a steady state error, okay, which is 100 RPM for this example. Okay, it's another important criterion for the time response. We can easily show the steady state error on unity feedback system or non-unity feedback system. We can easily show the block diagram of any system as like that. YS, and we have a unity feedback as like that. Where is the ES error signal? Of course here. Okay, ES is equal to RS minus YS. So we can write for the YS, RS minus, for the YS we can easily write ES times GS from this part. So if we collect the ES term on a side of the equivalent, we get 1 plus GS will be equal to RS. So ES, which is error signal, will be equal to reference signal over by 1 plus open loop transfer function, GS. So we can calculate this value in the time domain, limit S upper choose to 0 S times ES. So it will be represented with ESS, okay? Steady state. This is the steady state error. So it will be limit S upper choose to 0 S times RS over 1 minus 1 plus GS for the negative feedback system. Maybe we can do an example for this condition. Assume that we have a system which has 5 parentheses by S plus 1 divided by S squared S plus 5 S plus 12. This is the open loop transfer function for a unity feedback system. Find the ESS for unit step, unit ramp, and unit parabolic. Let's find it now. If the system is negative unity feedback, we have already know the steady state error formula as you see here. Let's get the ESS now. Will be equal to limit S upper choose to 0 S times weight. What is GS? 1 over 1 plus GS. Maybe we get before times with RS. We get before this part to easily calculate for all inputs. This part will be 1 over 1 plus 1 plus GS, as like that. So 1 over 1 plus GS will be equal to S to the power of 4 plus 17S cubed plus 60 s squared divided by s to the power of 4 17s cubed plus 60x squared plus 5s plus 5. So we can easily find the ESS now. Let's get RS unity step function. It means 1 over s. So ESS will be equal to limit s upper choose to 0 s times s to the power of 4 plus 17s cubed plus 60s squared divided by s to the power of 4 17s cubed 60s squared 5s plus 5 times with rs, which is 1 over s for the unit step function. What will be happen now? We can easily eliminate those ones, but we have still s terms on the denominator, so result will be directly 0. So we don't have an error, steady state error for the unit step input. What if we apply a unity ramp function? Rs will be 1 over s squared. So ESS will be equal to limit s upper choose to 0 s times, maybe we can get s squared parenthesis s squared plus 17s plus 60 divided by s to the power of 4 17s cubed 60s squared 5s plus 5 times with 1 over s squared for the unit ramp function. What we have now, s will be dismissed and also 1s here, it will be dismissed, but still, as you see, again we have an s term for the denominator. If you put s value as 0 for the limit 0 0 0 0 0 0, but still we have s term here, so the response will be 0. What if we have parabolic input, which is 1 over s cubed on the Laplace domain? ESS will be equal to limit s upper choose to 0 s times s squared plus 17s plus 60 divided by s to the power of 4 17s cubed 60 s squared 5s plus 5, and also we have 1 over s cubed. What we have now, s squared s cubed and s cubed. It will be dismissed as like that. So what we have now, 0 0 0 0 0 0 60 over by 5, it will be 12. 12. Yes, for the unit parabolic input, we have a steady state error, which is 12. Okay. But for the ramp, unity ramp function or unity step function, we have no steady state error. What if we have non-unity feedback system, such as RS? We have a transfer function GS, ys, and hs is the feedback gain. This is non-unity feedback function. Where is the es now? We cannot directly say now es is equal to ys over rs, because in here we have a feedback gain. So the dimension of the output and input can be changed. For example, assume that this is a position control of a DC motor. What is the output? Output is angle. What is the input? It can be maybe a voltage value. Okay, assume that voltage value. So the dimension will be different from each other. After the feedback gain, it will be the same, but we cannot say directly this point is E. Okay, so what should we do? Cannot say. What should we do? Maybe we can get the unity feedback block diagram from this system. How? Assume that we add a feedback here and the gain will be -1. If we have this kind of assumption, we have to add another feedback also, which should be 1, because that feedback will be dismissed and the dynamics of the system will not change. Okay, after do this operation, this part can be collected. How? Rs plus gs ys. In here we have now hs -1. One of them is like that, and the other of them is unity feedback. And what else? We can also collect all them. So what we have now, it should be rs plus g1s, assume that g1s, ys, and we have a feedback as like that. Now, as you see, this is a unity feedback system. So we can apply all of the rules on this system. But what is the G1S? We have a closed loop here. Here we have a closed loop. So we can easily say this GS over 1 plus GSHS minus GS. G1S can be calculated as like that. Okay, for this one we have an assumption. Okay, this assumption as the feedback gain HS does not have zero or zeros where at the origin. If we have for the HS a 0 or zeros at the origin, it will be changed. But we don't consider this condition. This is a special case. Okay. New example GS is equal to 1 over S square S plus 12, and HS is equal to 5S plus 1 divided by S plus 5. In here we can see HS has no zeros at the origin. Okay, so we can easily apply this system. What is the original system now? Let's draw it. First, we have 1 over S square S plus 12, and output a feedback gain, which is 5S plus 1 divided by S plus 5. First of all, we get the unity feedback. Let's find the G1S. Now, what is the G1S? It is important for the to find the steady state error. G1S is equal to 1 over S squared times S plus 12 divided by 1 plus 1 over, not 1 over, 5 S plus 1 S squared S plus 12 S plus 5 minus GS 1 over S squared S plus 12. We use this formula, okay, which is obtained before. We use it. Now we can arrange this formula, this equation, how? By multiplying by S squared S plus 12 S plus 5 for the both numerator and denominator. S plus 12 S plus 5. What we have now, maybe we can dismiss some ones. It will be dismissed, and in here we get S plus 5. What we have here, dismissed, but here we get S plus 5, and also for the 1 value we get all 1. So let's write it now. G1S will be equal to S plus 5 divided by S to the power of 4. If you dispatch this part, 17S cube plus 60S squared plus 5S plus 5 minus S minus 5. So finally we get S plus 5 S to the power of 4, 17S cube, 60S squared, 4S. That's all. Okay. Now we can easily get the ESS. For the ESS we need also 1 over 1 plus G1S. Please remember that. Where is it? Yes. As you see here, we need also this part. So we should find it before. It will be 1 over 1 plus S plus 5 S to the power of 4, 17S cube, 60S squared plus 4s. So finally we get s to the power of 4, 17s cube, 60s square, 4s divided by s to the power of 4, 17s cube, 60s square, 4s plus 1s more 5s plus 5. Okay, finally we get this. So what is the steady state error now? ESS will be equal to, for the first of all, 1 over s, which is unit step input. Let's evaluate this. Limit s approaches to 0, s times 1 over s from the reference signal times with s to the power of 4, 17s cube, 60s square plus 4s divided by s to the power of 4, 17s cube, 60s square plus 5s plus 5. Yes, what we have now, s will be dismissed as like that, but we have still s here on the denominator, so the response will be directly written as 0. Okay, what about the unit ramp input? Our s will be equal to 1 over s square unit ramp input. ESS will be equal to limit s approaches to 0, s times 1 over s square from the reference signal. Let me to copy this part to here. As like that. What we have now? Yes, 1s from dismissed here and 1s from dismissed here. We get 2 here and we get 3 here. So finally we have, if we apply s to the power of 0, 0, 0, 0, we have 4 here, 0, 0, 0, 0. So 4 over 5, finally we get 0.8. This is the steady state error for the unit ramp input. Yes, what's more, Rs may be 1 over s cube with its parabolic function. ESS will be equal to limit s approaches to 0, s times 1 over s cube from reference signal, and let me again to copy it here. What we have now, 1s is dismissed here, 1s is dismissed here, it will be 2 and 3. But here on the denominator we have one more s still. So the number over by 0, it will be infinity. Okay, so we can say this system will be unstable because we apply a finite input to the system, but we get infinite output from the system. So this system will be unstable. Yes, system is the same, but according to the test signal or input signal, steady state error can be 0, 0.8 or infinite, stable or unstable, as you see. Okay, all of them are important. Maybe we can continue from your lecture notes now. We can analyze this question on the time response also. Maybe where is the example here? It is the same example or not? Not the same. 5 times s plus 1. Yes, this example. Let's examine the time response of the system. As you see here, for the unit step input, founded value for the steady state error 0, for the unit ramp 0.8, and for the parabolic input, unit parabolic input, get infinite value. Yes, maybe we can evaluate also time response of this outputs. The output value, if we take the inverse Laplace of the ys, we can get as like that equation. What does it mean? What is the steady state value of this function? How can we get it? T approaches to infinity. When t approaches to infinity, in here we have an exponential term, so it will be 0, 0, 0, and 0. The remaining part only 1. What does it mean? Yes, the steady state value of the y is equal to 1. This is the steady state value. What is the steady state error? RT minus YSST actually. What is the RT? RT for this time response, unit step input 1 over S. What is the time equivalent of it? If they get inverse Laplace, 1. 1 minus 1, we get 0. So for this system, for the unit step input, we get 0 steady state error. Let's continue from unit ramp input. This is the time response of the unit ramp input. And when t approaches to infinity, this term will be 0. This term will be 0. This term will be 0. And this term will be 0. What is the remaining part? YSS will be equal to t minus 0.8. What is the RT value? RT value can be obtained as inverse Laplace of Rs, which is 1 over S square. So we can say it is T times, yes, RT is equal to, sorry, not T times T for the 1 over S square from the tierce Laplace. So what is the steady state error now? RT is T, steady state value of the output T minus 0.8, so it will be 0.8 as we found before. Yes, the last one for the unit parabolic input. When t approaches to infinity, this part will be 0 and 0 and 0 and 0. The remaining part YSS will be equal to 0.5 t square minus 0.8 t minus 11.2. What is the RT? Rs is equal to 1 over s cube. We assume that. So the inverse Laplace of it will give us RT, which is 0.5 t square. So the ESS will be equal to RT minus YSS. It will be 0.8 t plus 11.2. What does it mean? When t approaches to infinity, ESS will be infinity. So the system will be unstable.